In an alternating current, or AC, circuit, the current flows in both directions through a wire. This flow alternates between positive and negative half cycles. The electrons themselves don't fully reverse their direction completely. They drift back and forth within the wire. These electrons within the AC circuit are subjected to an electric field. This field prompts them to drift in a specific direction. During the positive half cycle, the electrons drift to the right. During the negative half cycle, they drift to the left. The statement that the relative motion of electrons at a specific point cancels out isn't entirely correct. While the macroscopic current alternates, a net movement of electrons still happens in one direction over a period of time. The electrons drift more during the positive half cycle because the electric field is stronger during this time. This allows current to flow. Think about a group of rowboats on a lake. If you row the boats back and forth, the water will slosh from one end to the other. Even though the boats don't move too far, the water, representing the electrons, still moves in one direction over time. In an AC circuit, electrons drift back and forth within the wire. However, they drift more in the direction of the positive half cycle. This net electron movement creates the alternating current. The relative motion of electrons at any given point might cancel out, but the overall current flow continues. Now let's delve deeper into the behavior of electrons within alternating current circuits. We'll explore concepts such as drift velocity, the role of the electric field, and how these factors contribute to the flow of current. Drift velocity is the average velocity attained by charged particles, such as electrons, in a material due to an electric field. In the context of alternating current, the drift velocity is not constant but varies with the alternating electric field. Even though individual electrons move randomly, the electric field causes them to drift in a specific direction superimposed on their random motion. The electric field is the force exerted on a charged particle per unit charge. In an alternating current circuit, the electric field alternates in direction, causing the electrons to drift back and forth. The strength of the electric field determines the magnitude of the force on the electrons and thus influences their drift velocity. The relationship between the electric field, the drift velocity of electrons, and the current can be understood through Ohm's law and the concept of conductivity. Conductivity is a measure of a material's ability to conduct electric current. It depends on the density of charged carriers, the charge of each carrier, and the drift velocity of the carriers. In alternating current, the conductivity remains constant, but the drift velocity and current vary with the alternating electric field. When considering the flow of electrons in a wire, it's important to distinguish between drift velocity and the speed of propagation of the electric field. The drift velocity of electrons is relatively slow, typically on the order of millimeters per second. However, the electric field propagates through the wire at nearly the speed of light. This means that the change in the electric field, and therefore the change in the direction of electron drift, occurs almost instantaneously throughout the circuit. In an alternating current circuit, the frequency of the alternating current determines how quickly the electric field changes direction. For example, in a 60 Hz system, the electric field reverses direction 60 times per second. This rapid change in direction causes the electrons to oscillate back and forth within the wire. The distance an electron travels during each half cycle depends on its drift velocity and the duration of the half cycle. However, as we discussed earlier, there is a net drift of electrons in the direction of the positive half cycle due to the stronger electric field during that period. The concept of displacement current is also relevant in understanding current flow in alternating current circuits. Displacement current is a term introduced by James Clerk Maxwell to account for the current that flows in a capacitor when the voltage across it is changing. Although there is no actual flow of charge through the dielectric of the capacitor, the changing electric field creates an equivalent current that contributes to the overall circuit current. The total current in an alternating current circuit is the sum of the conduction current, which is due to the movement of charge carriers, and the displacement current, which is due to the changing electric field. Understanding these concepts is crucial for analyzing and designing alternating current circuits. It helps in predicting the behavior of electrons within the circuit, understanding the relationship between voltage, current, and impedance, and optimizing circuit performance. Finally, let's consider some practical applications of the principles we've discussed. Firstly, in power transmission systems, alternating current is used because it can be efficiently transmitted over long distances at high voltages and low currents, reducing losses due to resistance. Secondly, in electronic devices, alternating current signals are used to transmit information, process data, and control various functions. Thirdly, in electric motors, alternating current is used to generate rotational motion by creating a rotating magnetic field. By understanding the underlying physics of electron flow in alternating current circuits, engineers can design more efficient and reliable electrical systems. This knowledge enables them to optimize the performance of electronic devices, improve the efficiency of power transmission, and develop new technologies that harness the power of electricity. In summary, the behavior of electrons in alternating current circuits involves a complex interplay of drift velocity, electric field frequency, and displacement current. While the electrons drift back and forth within the wire, there is a net movement of electrons in one direction over time, allowing current to flow. Understanding these concepts is essential for anyone working in the field of electrical engineering. Let's dive into some more specific aspects of electron behavior in alternating current circuits. We can consider the effects of different materials on electron flow, the role of temperature, and the impact of frequency on circuit performance. Different materials have different conductivities, which affects how easily electrons can flow through them. Conductors like copper and aluminum have high conductivities, allowing electrons to move freely with minimal resistance. Insulators like rubber and plastic have low conductivities, restricting the flow of electrons. Semiconductors like silicon have conductivities between those of conductors and insulators, and their conductivity can be controlled by adding impurities, making them useful in electronic devices. Temperature also plays a significant role in electron flow. In general, as temperature increases, the conductivity of metals decreases. This is because the increased thermal energy causes the atoms in the metal to vibrate more, which impedes the flow of electrons. In contrast, the conductivity of semiconductors can increase with temperature, as the increased thermal energy can free more electrons to conduct electricity. The frequency of the alternating current can also affect circuit performance. At high frequencies, effects like skin effect and impedance matching become more important. Skin effect is the tendency of alternating current to flow primarily on the surface of a conductor at high frequencies. This reduces the effective cross-sectional area of the conductor, increasing its resistance. Impedance matching is the process of designing a circuit so that the impedance of the source is equal to the impedance of the load. This maximizes the power transfer between the source and the load and minimizes reflections, which can cause signal distortion. In addition to these effects, the behavior of circuit components like capacitors and inductors also depends on the frequency of the alternating current. Capacitors store energy in an electric field, and their impedance decreases with increasing frequency. Inductors store energy in a magnetic field, and their impedance increases with increasing frequency. Understanding how these components behave at different frequencies is essential for designing circuits that operate correctly over a wide range of frequencies. Furthermore, the concept of reactive power becomes important in alternating current circuits with capacitors and inductors. Reactive power is the power that is stored and released by these components, rather than being consumed. It does not do any useful work, but it does contribute to the overall current flow in the circuit. Power factor is a measure of how effectively electrical power is being used. It is defined as the ratio of real power, which is the power that is actually consumed, to apparent power, which is the product of voltage and current. A power factor of 1 indicates that all the power is being used effectively, while a power factor less than 1 indicates that some of the power is being wasted due to reactive power. Correcting the power factor is important for improving the efficiency of electrical systems. This can be done by adding capacitors or inductors to the circuit to compensate for the reactive power of other components. In summary, understanding the behavior of electrons in alternating current circuits requires considering a wide range of factors, including the properties of the materials, the temperature, the frequency of the alternating current, and the behavior of circuit components like capacitors and inductors. By taking these factors into account, engineers can design efficient and reliable electrical systems that meet the needs of a wide variety of applications. Now let's consider the role of electromagnetic fields in alternating current circuits. When current flows through a conductor, it creates a magnetic field around the conductor. In alternating current circuits, the current is constantly changing, so the magnetic field is also constantly changing. This changing magnetic field can induce a voltage in nearby conductors, a phenomenon known as electromagnetic induction. Electromagnetic induction is the principle behind transformers, which are used to increase or decrease the voltage of alternating current power. A transformer consists of two or more coils of wire wound around a common core. When alternating current flows through one coil, it creates a changing magnetic field that induces a voltage in the other coil. The ratio of the voltages in the two coils is proportional to the ratio of the number of turns in the coils. Electromagnetic induction can also cause unwanted effects in alternating current circuits, such as electromagnetic interference or EMI. EMI is the disruption of electronic devices caused by electromagnetic fields. It can be caused by a variety of sources, including electrical equipment, radio transmitters, and cell phones. To reduce EMI, it is important to shield electronic devices and to use proper grounding techniques. Shielding involves enclosing the device in a conductive material that blocks electromagnetic fields. Grounding involves connecting the device to the earth, which provides a path for unwanted currents to flow away from the device. In addition to EMI, electromagnetic fields can also cause other problems in alternating current circuits, such as skin effect, which we discussed earlier. Skin effect is caused by the magnetic field induced by the current in the conductor. The magnetic field pushes the current towards the surface of the conductor, increasing its resistance. At very high frequencies, the skin effect can become so severe that the current flows only on the very surface of the conductor. This can significantly reduce the efficiency of the circuit. To reduce skin effect, it is important to use conductors with large surface areas, such as hollow conductors or conductors made of multiple strands of wire. In summary, electromagnetic fields play a crucial role in alternating current circuits. They are responsible for phenomena like electromagnetic induction, EMI, and skin effect. Understanding these phenomena is essential for designing efficient and reliable electrical systems. Let's turn our attention to the topic of power distribution in alternating current systems. Power distribution systems are responsible for delivering electrical power from generating stations to consumers. These systems typically consist of a network of transformers, transmission lines, and distribution lines. Transformers are used to increase the voltage of the power at generating stations and to decrease the voltage at substations and consumer locations. Transmission lines are used to transmit power over long distances at high voltages. Distribution lines are used to distribute power to individual consumers at lower voltages. The design of power distribution systems involves a number of considerations, including voltage regulation, power factor correction, and protection against faults. Voltage regulation is the ability of the system to maintain a constant voltage at the consumer's location, even when the load is changing. Power factor correction is the process of improving the power factor of the system to reduce losses and improve efficiency. Protection against faults involves using fuses, circuit breakers, and other devices to protect the system from damage caused by short circuits or other faults. In alternating current power distribution systems, there are two main types of systems: single-phase and three-phase. Single-phase systems are used for residential and small commercial applications. They typically provide power at voltages of 120 volts or 240 volts. Three-phase systems are used for large commercial and industrial applications. They typically provide power at voltages of 208 volts, 480 volts, or higher. Three-phase systems are more efficient than single-phase systems because they can deliver more power with the same amount of current. They also provide a more stable voltage and are less susceptible to voltage fluctuations. In addition to single-phase and three-phase systems, there are also direct current power distribution systems. Direct current systems are used in some specialized applications such as data centers and electric vehicles. Direct current systems can be more efficient than alternating current systems for certain applications, but they are also more expensive and complex. In summary, power distribution systems are essential for delivering electrical power from generating stations to consumers. The design of these systems involves a number of considerations, including voltage regulation, power factor correction, and protection against faults. Alternating current systems are the most common type of power distribution system, but direct current systems are also used in some specialized applications. Now we will delve into the topic of alternating current motors. Alternating current motors are electric motors that are powered by alternating current electricity. They are used in a wide variety of applications, from household appliances to industrial machinery. Alternating current motors are typically classified as either induction motors or synchronous motors. Induction motors are the most common type of alternating current motor. They work by inducing a current in the rotor, which creates a magnetic field that interacts with the magnetic field of the stator. This interaction causes the rotor to rotate. Induction motors are relatively simple and inexpensive, but they are not as efficient as synchronous motors. Synchronous motors work by synchronizing the rotation of the rotor with the frequency of the alternating current power supply. This is achieved by using electromagnets or permanent magnets on the rotor. Synchronous motors are more efficient than induction motors, but they are also more expensive and complex. Alternating current motors can also be classified by the number of phases of the alternating current power supply. Single-phase motors are used for small appliances and other low-power applications. Three-phase motors are used for larger industrial applications. Three-phase motors are more efficient than single-phase motors and provide a more stable torque. The speed of an alternating current motor is determined by the frequency of the alternating current power supply and the number of poles in the motor. The speed of a synchronous motor is exactly equal to the synchronous speed, which is given by the formula synchronous speed equals 120 times frequency divided by the number of poles. The speed of an induction motor is slightly less than the synchronous speed due to slip. Slip is the difference between the synchronous speed and the actual speed of the motor. Alternating current motors are controlled by using a variety of methods, including variable frequency drives, or VFDs, and soft starters. Variable frequency drives are used to control the speed of the motor by varying the frequency of the alternating current power supply. Soft starters are used to reduce the starting current of the motor, which can prevent damage to the motor and the power supply system. In summary, alternating current motors are electric motors that are powered by alternating current electricity. They are used in a wide variety of applications and are classified as either induction motors or synchronous motors. The speed of an alternating current motor is determined by the frequency of the alternating current power supply and the number of poles in the motor. Alternating current motors are controlled by using a variety of methods, including variable frequency drives and soft starters. Now let's explore alternating current generators, which are devices that convert mechanical energy into electrical energy in the form of alternating current. These generators are fundamental to power generation in most power plants, utilizing various sources of mechanical energy such as steam turbines, gas turbines, hydro turbines, and wind turbines to drive their rotors. The basic principle behind alternating current generators is electromagnetic induction, which states that a changing magnetic field induces a voltage in a conductor. In an alternating current generator, a rotor containing a set of conductors is rotated within a stationary magnetic field produced by the stator. As the rotor turns, the conductors cut through the magnetic field lines, inducing a voltage in the conductors. This voltage alternates in polarity as the conductors move through different regions of the magnetic field, resulting in the generation of alternating current electricity. Alternating current generators come in various types, including synchronous generators and induction generators. Synchronous generators are the most common type used in large-scale power generation due to their ability to maintain a constant frequency and voltage output, as well as their ability to provide reactive power for voltage support in the power grid. Induction generators, also known as asynchronous generators, are simpler in design and are often used in smaller scale applications such as wind turbines and micro-hydro systems. However, they require an external source of reactive power for excitation and are more susceptible to voltage fluctuations. The output voltage and frequency of an alternating current generator are determined by the speed of rotation of the rotor and the number of poles in the generator. The voltage is directly proportional to the speed and the magnetic field strength, while the frequency is determined by the speed and the number of poles according to the formula frequency equals number of poles times speed divided by 120. To maintain a stable output voltage and frequency, alternating current generators are equipped with control systems that regulate the speed of the prime mover and the excitation current in the field windings. These control systems ensure that the generator operates within its design limits and responds quickly to changes in load demand. In addition to generating electricity, alternating current generators also play a critical role in stabilizing the power grid by providing inertia and damping to the system. The inertia of the rotating mass of the generator helps to resist sudden changes in frequency, while the damping provided by the generator's control system helps to suppress oscillations and prevent instability in the grid. Furthermore, alternating current generators are equipped with protection systems that detect and respond to abnormal conditions such as overvoltages, overcurrents, and faults. These protection systems are designed to quickly isolate the generator from the grid in the event of a fault, preventing damage to the generator and ensuring the safety of personnel and equipment. In summary, alternating current generators are essential components of modern power systems, converting mechanical energy into electrical energy in the form of alternating current. They come in various types, including synchronous generators and induction generators, and are equipped with control systems and protection systems to ensure stable and reliable operation. These generators play a critical role in maintaining the stability and reliability of the power grid, providing inertia, damping, and protection against faults.